Welcome to this class on hardware security. So, we shall be continuing our discussions on elliptic curve cryptographic hardware design. In particular, today we shall be trying to look into more details about the hardware that we started discussing in the last class. So, we shall be starting to look into the ALU design, that is arithmetic logic unit design. We shall be trying to take a more detailed look into the control unit design and the final inversion, along with a quick discussion on the top level scalar multiplication and also how to verify the design. Okay, that is the methodology that we adopted for in our case. So, this is a quick recapitulation of the projective point arithmetic. So, as we said already that the projective point arithmetic was introduced to reduce the number of costly inversions which are required in the underlying finite field operations. So, here are some equations on the point doubling, that means when you are trying to double a point on the elliptic curve in projective coordinates. As you can see, right, that there are some multiplications which are involved in this step, and in our design, right, if you remember the data path, we had a constraint of having only one multiplier. So, therefore, we have to basically try to kind of multiply or essentially perform our operations with one multiplication at a time. So, our strategy will be that we will be ensuring that one multiplication is at least used every clock cycle. That means, the multiplier is not sitting idle in any clock cycle. So, this is just to reduce the number of clock cycles. So, in this case, for example, we can see that if I schedule the operations, okay, so one of the important steps that we need to kind of look into is how do you schedule these operations. That means, how do you do these operations step by step. So, in this case, we require 4 time steps to do the operation. Okay. And here are the corresponding steps which are detailed. So, these are essentially nothing but, so this algorithm is nothing but essentially a depiction of how these steps would be performed. Okay. So, more detailed look into this can be seen here in context with our data path for the arithmetic unit. So, you can see here that if you are interested to say like for example, do these steps, like suppose these are the individual like successive 4 clock cycles, clock 1, clock 2, clock 3 and clock 4. So, you see that in our arithmetic unit there are 2 output ports, C0 and C1. This is for parallelism. So, we are trying to extract as much parallelism as we can, okay, given the constant that we have got one multiplication or one multiplier. So, here therefore, right, when we are doing say when you are doing this computation like RA1 square into RC1 square. So, you are basically you are occupying your multiplier, but at the same time you can see that in my data path there are some other peripheral circuits like addition, squaring, okay, and like when 2 squarings are successive, then you can also raise an element to a power of 4. Okay. So, therefore, these kind of computations are kept so that you can essentially do it very much independent of the multiplier, okay, and they are also less in terms of cost. So, you can essentially provide dedicated support for them. Okay. So, you have to basically plan this entire circuit. So, essentially the crux of the design lies in how you can like nicely develop an architecture. Okay. So, that essentially is a sort of thing that we only gather out of trying few examples or through experience, but you can essentially get certain you can try to understand the relationship between the operations that we need to do and the final circuit that we have at hand. Okay. So, let me try to detail, for example, like and at least try to understand how to read these tables basically. Okay. So, you can see that there is in this table we basically detail the input and output of the register file for point doubling, because the register file, as we discussed yesterday, works hand in hand with your arithmetic unit. Okay. So, the arithmetic unit basically receives some inputs from the register file, does some computation, and the result is again stored back in the register file. So, that means C0 and C1 and Q out are again stored back into the register file. So, if you see here, the register file had outputs like A0, A1, A2 and A3, okay, and it produces A0 and A1 in these 2 buses. It floats the data of RA1 and RC1. Okay. So, now RA1 and RC1 are essentially the first registers of the first and the third register banks. Okay. So, RA1 stores the value of x1, okay, and RC1, and actually RA1 stores the so RA1 stores the coordinate x1 and RC1 stores the coordinate z1. Okay. So, that means it is basically what you are doing now is that when you want to say multiply RA1 square into RC1 square, that means this multiplier should receive through this multiplexer the inputs A0 square and A1 square. basically. Okay. So therefore, A01 square and A1 square should be passed in as an input. The multiplier will develop this result, and if you see this output, right, needs to be multiplexed out. Okay. So I will again come back to this when we talk about the control path or the control signals. Okay. But this is something that we need to do, and this tearing out information or data should be done by the control logic. Okay. That means the select lines of the multiplexers will be switched accordingly to our control logic. Okay. And therefore, right, we essentially have a clean separation of the data path and the control path, which is desirable in any good architecture design. So finally, right, we have got this result. That means, for example, we calculate, say, like x1 squared into z1 squared. This is essentially performance of this step. And in parallel, you are also performing RC1 to the power of 4. So that stands for Z1 to the power of 4. Okay. So therefore, right, we are also calculating, if I may write, like that, we are also calculating RC1 to the power of 4, and that is essentially nothing but this operation, that is Z1 to the power of 4. Okay. And this operation is essentially this operation, that is x1 squared into z1 squared. So you see that these two things are performed in the same clock cycle in this architecture. Likewise, right, in the next clock cycle, we perform this computation, that is RB3 into RB4. So RB3 is nothing but z1 to the power of 4, and if you remember, RB4 was used to store the curve constant b. Okay. So that means b into z1 to the power of 4 is performed in this computation, and b z1 to the power of 4 is there in few other places also. So therefore, this result is ready, okay, with us in RB3. So in the next clock cycle, we basically kind of calculate this part, that is, we basically like in the first in this computation, we perform this part, that is, we add, remember that a is 1, so we basically add z4 with y1 squared with b z1 to the power of 4. So b z1 to the power of 4 is already ready in RB3. Okay. So therefore, the RB3 essentially stores the value of b z1 to the power of 4. You add that with RB1 squared. So RB1 squared is nothing but your y1 squared. Okay. And a z1 to the power of 4, a being 1, is equal to z4. Okay. So therefore, this result is already ready with us, and essentially this is stored in RC1. Okay. So therefore, right, you essentially have these three things ready, and the other part is again, like this part, that is RA1 to the power of 4 plus RB3. Okay. So this is essentially trying to basically compute this part. So therefore, essentially this is nothing but raising x1 to the power of 4 and adding that with RB3. Okay. So therefore, in the final clock cycle, you just need to add this component. So therefore, you need to add this component with this result. Okay. So remember that we already had this RC2 ready in the previous clock cycle. So we just add RB3 into RC1. So RB3 into RC1 stands for this part of the computation, because you already have RB3 storing bz1 to the power of 4. You multiply with this component to get this part. Okay. So therefore, this pretty much kind of explains how the 4 clock cycles work, and you essentially perform the doubling operation. Okay. So I did not like derive these equations in the Lopez-Dahab coordinates, but I leave it to you as an exercise to do this do this calculation. Rather, I will be trying to like explain how the addition works, because that is slightly more complicated, and we will try to see how the equations work in that case. So these are my projective point addition operations, and essentially this looks little bit more complex than the doubling equations. Okay. So we will try to take a look into that derivation. So let me try to explain that, and so therefore, right, if you remember the original affine coordinate equations. So the original affine coordinate equations were as follows. You had x3, which is equal to, so I will write or use lambda to store the slope in this case. So lambda square plus lambda plus x1 plus x2 plus a. Okay. So and likewise y3 was equal to lambda into x3 plus x1 plus y1 plus x3, and lambda is the slope. So in this case, it is y2 plus y1. Remember, it is in characteristic 2. So divided by x2 plus x1. Okay. So now for projective coordinates, we will make these. So remember, it is a Lopez-Dahab projective coordinates. There are different projective coordinates. So we will be using the Lopez-Dahab projective coordinates, where small x1 is mapped into capital X1 by Z1 and x3 is mapped into capital X3 by Z3 and small y1 is mapped into y1 by Z1 square and small y3 is mapped into y3 by Z3 square. So, now with this replacements or substitutions, you can again look into the value of lambda. So, lambda is now equal to so remember what we will do is that we will do this operation in affine coordinates. Okay. So, I will be keeping y2 as it is. So, y2 will remain in its affine coordinates. So, rather this operation is done in mixed coordinates. So, the y2 is remaining in affine coordinates and the other one will be in projective coordinates. So, we will write y2 plus y1 by z1 square divided by x2 plus x1 by z1. Okay. So, that turns out to with little bit of like simplifications, y2 z1 square plus capital Y1 divided by z1 into x2 z1 plus capital X1. Okay. So, therefore, we will write here that let A hold the value of y2 z1 square plus y1 and B hold x2 z1 plus x1, okay, and let C hold z1b. Okay. So, let C hold z1b. So, in that case, therefore, lambda becomes nothing but A divided by z1b, A divided by z1b. Okay. So, therefore, with this derivation we have got x3 small x3 equal to capital X3 divided by z3, right. So, that is equal to so we are basically having this equation for x3. So, we are basically trying to calculate the value of x3, but remember that x3 is equal to lambda square plus lambda plus x1 plus x2 plus a. So, that is essentially given by this formula. So, we basically can write now therefore, using this value of lambda, because remember this is my expression for lambda. So, I can write this as A divided by B z1 square plus A divided by B z1, okay, plus x1 by z1 plus x2 plus A. Remember x2 small x2 remains in the affine coordinates. So, therefore, this essentially is nothing but B z1 whole square in the denominator. The numerator is A square plus AB z1 plus B square x1 z1 plus B square small x2 z1 square plus A B square z1 square. So, therefore, what we will say is that z3, this implies that since x3 is equal to x3 by z3, z3 is equal to b z1 whole square, and that is equal to also c square, because c is z1b, okay, and capital X3 is equal to a square plus ab z1, okay. This we can write as ac, because c is z1b. So, a square plus ac plus b square x1 z1 plus b square small x2 z1 square plus ab square z1 square, and that is equal to again a square plus ac plus, see, I can take b square common from all sides this. So, I can write this as b square x1 z1. So, actually I can probably write this also as, I can take z1 common and I can write x1 plus x2 z1, okay, plus a z1 square, okay, and this I can write again as a square plus ac plus b square Z1 B, because see that this part is nothing but already B, which is essentially as written here. Okay. So, this is my capital B. So, I can write this as B square into Z1 B plus A Z1 square. Okay. So, therefore, right, I mean we have a more or less compact equation, and we have to kind of remember that these are all the intermediate steps which you are calculating when you are doing your addition operation. Okay. So, likewise you can derive the equation for y3. Okay. So, and you can again do that. So, I will try to like derive the equation for y3. So, one thing you can observe that what I can also do few more substitutions here, just to, for example, this AC I can write as, say, like E is equal to AC, E equal to AC, and D is equal to B square Z1 B plus A Z1 square. Okay. So, if I write this, then X3 becomes equal to A square plus E plus D, right. This is the more compact expression for X3. Okay. Likewise, you can derive for Y3. Okay. So, let us do this after this. So, I will be clearing this part and again looking into how to derive for Y3. Okay. So, Y3 is is equal to Y capital Y3 divided by Z3 square. Okay. And that is equal to A by Z1 B, so divided into X1 by Z1 plus X3 by Z3 plus X3 by Z3 plus Y1 by Z1 square. So, this actually follows from the equation of Y3. So, if you remember that Y3 was equal to lambda into X3 plus X1 plus Y1 plus small x3. Okay. So, now you are transforming them into the projective domain, okay, and using the value of lambda and the other things that we already saw. So, you can essentially write Y3 in this form, and therefore, write again do a similar thing that we did for X3. You can write the denominator as so this is nothing but writing the denominator as Z3 square. So, Z3 square, and then writing this as AB cube X1 Z1 square plus AB X3 Z1 plus X3 Z3 plus b to the power of 4 Y1 Z1 square. Okay. Right. So, so therefore, right, I mean if you have these components, then now you can write therefore Y3 as AB cube X1 Z1 square plus AB X3 Z1 plus X3 Z3 plus b to the power of 4 Y1 Z1 square. Okay. So, now note that we already had this in the previous derivations, that capital X1 was equal to B plus X2 Z1 and E was equal to AB Z1. Okay. And also that Z3 was equal to B Z1 whole square. Okay. So, therefore, write Y3 is equal to A b to the power of 4 Z1 square, okay, plus E small x2 Z3 plus capital E x3 okay, plus a capital X3 Z3 plus b to the power of 4 Y1 Z1 square. Okay. So, this is just substituting this AB Z1, we are substituting E here, okay, and we have got E x3 because of that, and the other term is so that is E x3 is a ex3 z1, and you also have got here this part. So, this part you are getting by from this equation. Okay. So, capital X1 you can actually substitute as b plus x2 z1. Okay. So, if you substitute b plus x2 z1, then you will have b to the power a b to the power of 4 z1 square coming up as one part. Okay. And likewise, so you can just verify this, that is, if I for example write ab cube z1 square, and instead of capital X1, that is this part, I write b1 or b plus x2 z1, then I have got a b to the power of 4 z1 square plus ab cube, and so I have got ab cube z1 to the power of 3. Okay. So, this part essentially, right, I mean yeah, so this part should get cancelled out, right, with your second term, right, that is this term. So, like we derive the steps for x3, we will be deriving the equation for y3 in a similar manner. Okay. So, if you remember, right, I mean the equation for y3 that we had in the previously when we stated the equation for y3, we had y3 equal to lambda into x3 plus x1 plus y1 plus x3. Okay. And we derived that lambda we wrote in a compact format was a by z1b. Okay. And also we had like seen that z3 in the when we derive the equation for x, right, we had z3 equal to b square z1 square. Okay. So, therefore, right now we can write y3 in a similar way. We can write y3 in the projective coordinate as y3 divided by z3 squared, and that is equal to a by z1b into x1 by z1 plus capital X3 by z3 plus x3 by z3. So, that is from this term, and plus y1 by z1 square. So, that is from this term. Okay. So, therefore, now we essentially can break this up into parts. So, we can write this as a x1 divided by z1 square b plus a x3 divided by z1 z3b plus x3 by z3 plus y1 by z1 square. Okay. So, now we can multiply the numerator denominator here by b, and you see that if I do that, then I get b square z1 square, and that is equal to z3. Okay. So, therefore, I can write the denominator as z3, and that means that I have multiplied the numerator also by b. So, that I have got a x1 b. Okay. Plus I have got a x3, and I multiply again the numerator and the denominator by in this case z1b. Okay. So, if I multiply by z1b, then I have got z1b whole square in the denominator, and z1b whole square means z3. So, I have got another z3. So, this becomes z3 square plus again I multiply x3 z3 by and I get z3 square here plus y1 b square, and this becomes z1 b square. So, that is again equal to z3. Okay. So, now we can take z3 square in the denominator, and therefore, the numerator becomes ax1 b z3 plus ax3 z1b, this does not change, plus x3 z3, this also does not change. This becomes multiplied with z3, y1 b square z3. Okay. And that is equal to, if I write in the numerator again, remember that I have got z3 as equal to b square z1. So, if I plug that back, then I have got a x1. Okay. And so, if I just plug in back z3 as b square z1, okay, then I have got I can write here this part as a b to the power of 3 z1 square x1, okay. So just writing the x1 in the at the end, plus AB x3 z1, okay, plus this part again if I bring in, so this part let me write as x3 z3, and for this part I have got, if I bring in and substitute in place of z3 b square z1, then I have got b to the power of 4 y1 z1 square divided by z3 square, okay. So therefore, right, I have got this numerator, right, essentially is nothing but is essentially y3. So this is my equation for y3, okay. So let me just use it and try to see that whether we can, let's try to simplify this equation, and for that I will be using another, sorry, so let me just clean this, one second. Yeah. So let me just clean this up and write it as, or clean the equation. So we have got y3 is equal to ab cube x1 z1 square, okay. So ab cube x1 z1 square plus ab x3 z1 plus x3 z3 plus b to the power of 4 y1 z1 square, okay. So now we will make few substitutions. So for example, note that x1 or capital X1 is equal to b plus x2 z1, and E is equal to ab z1, okay, E equal to ab z1, and we also have, as already we noted, that z3 is equal to b z1 whole square, okay. So therefore, write y3 is equal to, if I do this, then y3 is equal to a b to the power of 3, okay, a b to the power of 3 z1 square, and I, instead of x1 I can write b plus x2 z1, okay, plus plus E capital X3, okay, plus x3 z3 plus b to the power of 4 y1 z1 square, okay, and this is equal to a b to the power of 4 z1 square, okay, plus plus E x2 z3, okay. So E x2 z3, because you know that z3 is equal to b squared z1 squared, so therefore you can get it from here, okay, and you can also plug in E equal to ab z1, okay. So you will get E x2 z3 plus E x3 plus x3 z3 plus b to the power of 4 y1 z1 square, okay, and that again you can write as this, you can write this as y2 z1 square plus y1 b to the power of 4 z1 square being taken common, okay. So that essentially comes from the equation that we have for A, okay, and this plus E x2 z3, okay, plus E x3 plus x3 z3 plus b to the power of 4 z1 square y1, okay. So this becomes equal to y2 z3 square plus E x2 z3 plus E x3 plus x3 z3, okay. So So, this essentially, right, I mean you can see that b to the power of 4 z1 square and y1 square. So, these two terms cancels off, and this is essentially the term that I have, okay, finally. So, then I can also write few more substitutions, like say g is equal to x2 plus y2 into z3 square, and f is equal to x3 plus x2 z3. With this I can write therefore that y3 is equal to g plus x2 z3 square plus e x2 z3 plus e x3 plus x3 z3, and that is equal to g plus f into e plus z3. Okay. So, that gives you the final equation for y3. So, we already had x3, we had z3, and now we also can calculate y3. So, we have basically all the components for the addition equation. So, now let us get back to the slide and try to see that these are the equations. So, this is essentially just starting from the bottom. So, you can see that this is your y3 equation, that is exactly what we defined here. Okay. So, e plus z3 into f plus g. Okay. Likewise, we already had z3 as c square. Okay. And also you can verify the other equations step by step, essentially it tallies with our derivation. Okay. So, therefore, we have now the equations, and now once we have these equations, right, we have to see like how many clock cycles are required given the constant that we have got 1 multiplier. It turns out that in this case we require, if you do at scheduling, right, we require 8 clock cycles to perform this operation compared to your doubling where you had 4 clock cycle requirements. So, here you can see again, like you can verify that if I have got 2 outputs in parallel which I can produce. So, every clock cycle I am using 1 multiplication, the multiplier is always used in every clock cycle. So, you can see that every time it is used. The other component or other output is often used to do peripheral computations. Okay. So, in that case you have got 8 time steps which are required. So, let us take a look at the control unit. Okay. In the control unit you will see that we basically have got like the data flow, basically essentially like for doing the entire scalar multiplication we will have 4 distinct parts. Okay. The first part will be the initialization part, where you initialize your like the base points and the constants for the curve. In the second part you do the doubling operation, depending on doubling you always do. So, doubling you expend like 4 clock cycles. So, that are shown by these blue circles, and that is followed by the 8 clock cycles which are required for doing addition operations. Okay. But this is conditional in this architecture. Okay. Later on we will see this is not a very secured way of doing it, but at least from performance point of view this looks fine. So, you do basically take 8 clock cycles for doing the addition. And once you have done all these things, right, then done or process the entire scalar, you go for the final result where you get the affine coordinates and you get back the ultimate result, and for that you do an inversion. So, that essentially is shown by these brown circles. Okay. And for the inversion we will see that we have got 24 clock cycle requirements. Okay. That is done by the Ito-Suji inversion algorithm. So, these are the different components for doing the operation. So, you have got various steps. So, let us try to see at least how to read the control logic. Okay. I will not go into too much details about that, but rather leave to you as an exercise. But you can see that pretty much you essentially have got all the components which are required. So, let us explain the control unit, which is the essentially the the centered stone of the architecture. So, the control unit has got 4 distinct parts. So, that is shown by this FSM or finite state machine. So, you can see that I have got we have drawn like using the green color, we have written the initialization portion where you load the initial curve constants and the initial base point, followed by the doubling operation which is shown by the blue circles. Okay. And the doubling is done always, but and there are 4 clock cycles we are required for doubling because of the reason that I said. And subsequently, right, you have got 8 clock cycles required for doing the addition operation. Okay. And the addition is done conditionally in this architecture. Later on we will see that this is not a very secured way of implementing things, but at least from performance point of view this looks fine. And then there is a final step of inversion where you get the final result, you bring the result back from the projective to the affine coordinates and also get the result. So therefore, this is shown here in the brown line, and there are turns out to be 24 clock cycles which are required when you are doing Ito-Suji inversion algorithm or employing the Ito-Suji inversion algorithm as we have studied previously. So here is a snapshot of the control logic. You can see that there are 3 initial blocks cycles. There are 4 like the doubling steps, and there are like 8 addition steps. Okay. So let us see how the control logic is decided. So with this example, so for this you have to see or keep in perspective the entire data path. So here we show, first of all, in this cycle, in this architecture we show the register file, and this is the arithmetic unit. Okay. And then these are the corresponding control words and also the corresponding logic for doing the computations. Okay. So let us try to take some examples, like for example the initialization block. Okay, if you take the initialization block, and in that case you will see, and in particular I am concentrating on the second register file. So you will see that the second register file is stored or storing the essentially is processing on the y coordinates. Okay, so if you observe the steps here, then you get RB1 equal to PY. In the second clock cycle you do RB2 equal to PY. Okay, so therefore that means you are writing into RB1, here you are writing into RB2. Okay, so now if you see the logic here, that means when you are wanting to write into RB1, so as I said that the first address or address 1 is used to choose the write address. Okay, and address 2 is used to choose the read address. Okay, so address 1 is essentially controlled by C14 and C13. Okay, and the read address is stored by C16 and C16 and C15. Okay, so that is shown here by this small thing. Okay, and if you can observe here, then you can see that the corresponding control here initially, right, is essentially C14 and C13, and that shows 0 0. Okay, if it shows 0 0, that means you are basically writing into the first register here, that is RB1. Okay, and that is exactly what you are doing in the equation. In the second clock cycle you are writing into RB2, and that means that this control should be changed into 0 1, and that is what is done here. Okay, and in the third step you are basically writing into RB4, so RB4 should be 1 1. Okay, so that is what is done here, is 1 1. But in all these things, right, you can see that the read address is don't care, because you are not reading anything. Okay. Likewise, if you see the doubling, the first clock cycle for doubling, so in this case, right, when you are doubling, then the operation which you are doing is RA1 square into RC1 square. Okay. So that means, right, the data has to be passed into the multiplier, and that means these select lines will become functional. Okay. So that means now if you see, right, I am basically taking the input from RA1, so that is essentially stored here. So what I do is I basically write, and this is the corresponding control for marks A and marks B. So these are the 2 input multiplexers to the multiplier circuit. So here I need to choose, therefore if I want to multiply this, I have to choose the corresponding so these are the corresponding output results which are being generated from the arithmetic unit. Okay, so now you can see that what I want to multiply is RA1 square into RC1 square. Okay, and that is here essentially your A0 square and A1 square. Okay, so therefore you will see that the control logic here, that is the marks A and marks B, their select lines are 0 0 1 and 0 0 1. So 0 0 1 means the second line of the multiplex of the inputs. Okay, so you are basically selecting, if you can see the input is A0 square and here it is A1 square. So that means A0 is coming and A1 is coming, they are getting squared by the squared circuit in my arithmetic unit, and I am passing A0 square and A1 square to the multiplier. So the multiplier multiplies them and the result is ready in the bus M. Okay, so this is the corresponding bus M where the result is stored. So if you can observe, right, that this is your final result where you are getting the output. So this output needs to be multiplexed out. So therefore, right, that means this select line should be set to 0 0 at that point. Okay, and that is precisely which is being done here. If you observe, then you will see that C6 and C7 and C8 and C9, that means these are the corresponding control logic. So these 2 bits, right, are 0 0 here, which means that the multiplier is getting passed. So that means this output is getting computed and getting passed out, is basically passed in C0 bus. The other output is RC1 to the power of 4, which you need to pass to C1, that is C1 is this bus. Okay. So, if you see the inputs here, and out of them write a1 to the power of 4, this input is what I need basically, and therefore I need to pass this out as an output. So, therefore, write 0, 1 and 2. So, therefore, this line needs to be made 1, 0, and that is essentially done by this control where you make it 1 and 0. Okay. So, this kind of explains how you basically set the control, so that you basically configure, and all these steps essentially are done in a similar fashion, which I leave you to be an exercise. You can verify each of these steps and you can try to understand their correlations. So, with this background, right, we now can go into, or just have a look into the Verilog code without going into too much details. So, this is nothing but a depiction of how the controller works in. So, you can see that this is the output logic, because the controller essentially generates an output which is nothing but the control signal. Now, that depends upon two things. It depends upon typically on the state. So, essentially you basically have the state. So, you have basically encoded all the steps in states, and depending upon the state you produce an control word. Okay, and the control word is nothing but the binary value of these 1, 0 configurations. Okay, so that is essentially stored by these funny looking hex characters. Okay, there is nothing but their binary representations. So, likewise you essentially can write for all of them, like these are the initial parts, these are the doubling parts, and this is the corresponding addition state. So, all of them, their control logic has been created or modeled in the Verilog code. Finally we have an inversion step, because after you have done doubling, addition, and the entire thing is ready, you need to do the inversion to get back the fine results. Okay. So, I will just quickly recapitulate you about that Itosuji inversion algorithm using the quad logic which we studied previously. So, this is a quick flow chart about how this computation works in, and if you remember, like I will just show you like one part. For example, this is the initial step where you need to do a cube. Okay. So, in a cube basically I take the input, but remember I do not have any cubing circuit, but I have got a squaring circuit. So, what I do is I take a1, I pass it just as it is here, I take a1 and now I square it and pass it here, a1 square. I now use this hybrid Karlsruhe multiplier to do this multiplication. Okay. So, therefore, right, when I am multiplying this, I have to choose the fifth input here, and I have to, you can count 1, 2, 3, 4 and like so 0, 1, 2, 3, 4 and 5. So, that is the fifth input. So, it should be 1, 0, 1. Okay. And that is essentially exactly what is here. So, therefore, if you observe this in this part, it is 1, 0, 1, and the first part is 0, 0, 1, which means it is the second input from here. So, you are choosing the fifth input here and the second input here, and they are being multiplied by the multiplier. So, therefore, you need to again pass it to the output by accordingly choosing this control logic. So, that is exactly how these operations are done, and finally, you get your results. So, you can essentially perform all the successive steps in a similar fashion, okay, and get the entire computation being done. So, likewise, there is another step which we have shown here. It is the final quadding step, where you see that in one step I raise something to the power of 4 to the power of 3. Okay. So, if you remember the quad block, in the quad block there is a select input. Okay. The idea is that if the select input is made 3, that means if I made this 3, and if this is alpha, this output is alpha to the power of 4 power of 3. Okay. So, therefore, right here what we do is exactly that. So, you see the select value. The select value is made 3, it is 0, 0, 1 and 1. So, it becomes 3, and therefore, you calculate alpha to the power of 4 power of 3. Okay. So, therefore, right, I mean that explains all the individual components, and finally, right, this is an example of how you can of the Verilog program or the Verilog model for the quad block. So, you see that there is a select line, and depending upon the select line you have an internal quad block through which you calculate this. You can verify later on, and if you see the quad block, just remember the architecture. So, in this the Verilog model, we just place these quad circuits one after the other. If you remember that we had 14 cascade stages. So, these are the 14 cascade power blocks which have been placed. All of them calculates power to the power of 4. Okay. Depending upon the select, you basically multiplex any one of them out. For example, if I want to select something intermediate, then I can just choose one thing from this. For example, if I want to calculate alpha to the power of 4 power of 3, right, then that means that I have to basically take this. So, this is my alpha, this becomes alpha to the power of 4, this becomes alpha to the power of 4 square, this becomes alpha to the power of 4 power of 3, and now I make this 3. So, therefore, this gets selected out. So, it becomes alpha to the power of 4 power of 3. Okay. So, now that is essentially written here, and this is the final selection module. So, which says that how you are essentially selecting. So, therefore, if your select line is 3, then you basically select this line, okay, which you can implement easily through a multiplexer routine. So, finally, right, I mean that essentially explains pretty much the logic, and essentially, right, finally this is your power 4 circuit, which is exactly analogous to your squaring routine. It also does the modular reduction in one go inside this code. Okay. And you can also observe that the entire architecture just has XORs, because power of 4 in characteristic 2 field is a linear operation. So, essentially you do not need any explicit AND gates, you can do the entire operation just by using exclusive ORs. So, finally, you have got the scalar multiplier. So, in the scalar multiplier you have got these essentially the recapitulation of your double and add algorithm. So, how do you implement the state transitions? Again, this is a recapitulation of your finite state machine. So, you can observe that the state transition, that is the next state logic, can be easily observed or written in Verilog by this always encapsulation. So, what you can do is that depending upon your current state, you essentially determine your next state. Okay. So, in all this entire thing, it is pretty much that it goes into the next state depending upon your current state, except for this key logic where you have a jump. Okay. So, that essentially is this part where you have a conditional key statement, and depending upon that, from this clock cycle, I mean you either you do a doubling, and you follow a doubling with a doubling, or you go into the addition step basically. So, you either go from here to here, or you go from here to here, okay, and that depends upon your key bit. Okay. So, finally, right, when you make a complicated design, you have to verify your design. So, it is very important that you check that your result is correct. You should basically verify it with a different kind of implementation. So, typically we write a software program, and then we verify that our circuit is correct with respect to the software program. In this case, you can use this reference that we used by a book by M. Rosing. It is called its implementation of elliptic curve cryptography, and from there you can get certain references, and if you look into it, you can get an elliptic curve code on different fields, and you can verify your result with respect to it. So, finally, right, to conclude this part, these are some of the references that we have used. In particular, this is a nice paper by Lopez and Dehab, which was written in Chess in 99. And there are some other interesting texts also, which I have kind of summarized here. And this entire program, that means the entire Verilog code for the elliptic curve processor, you can get in this link. So, you can just download this link and look in more details about the about what we probably could not discuss in the class. And these are again some of the references that we have used. In particular, there is a very nice book on elliptic curves, and this is also very standard textbooks on elliptic curve implementations and elliptic curve discussions. You can also get into or look into this book, where this design is detailed in much more in much more content, and these are also some nice books on elliptic curves. For example, this is also a very nice book on elliptic curve, which you can have a look into. So, to conclude, what we discussed is about different scalar multiplication algorithms. We discussed about an LSB first versus MSB first approaches, and we compared them. We discussed the Montgomery ladder for scalar multiplication. We discussed how to implement such ladders without using the y coordinates explicitly. We discussed on projective transformation of the ladder. We discussed on parallelization techniques for the ladder. We discussed complete end-to-end implementation of an ECC processor. So, that roughly takes us to the end of the discussions on elliptic curve hardware. So, in the next class, we shall be trying to see that performance is not the only factor. There are many other things like security of implementations which we need to take care. So, that will bring us to the topic of what we call as side channel attacks, which we will try to take up from the next class. Okay. Thanks for your attention.